Hello students, welcome to EPG Pathshala. I am Anu Sharma from Kurukshetra University, Kurukshetra. Today we are going to discuss about the module External Fields, the Zeeman and Stark Effects from the paper Atomic and Molecular Physics. So students, let us see what we are going to learn in this module. In this module, effect of external static magnetic and electric field on atoms will be discussed. We will be discussing influence of weak static magnetic field called Zeeman effect. The effect of strong magnetic field on atoms called Paschen-Back effect will also be discussed. Effect of static electric fields on atoms called Stark effect will also be discussed. In this module, we consider the effect of external fields on atoms. This table defines the nomenclature of the effects that we shall be considering. We shall start by looking at magnetic fields. When magnetic fields are applied on atoms, two types of effects are seen. One set of effects are seen when the value of magnetic field is low. These are known as normal Zeeman effect and anomalous Zeeman effect. The second effect seen under the influence of magnetic fields is the Paschen-Back effect. So first of all, we will be considering the effect of magnetic fields, and then we will move on to consider the effect of electric fields on atoms. This effect of electric fields on atoms at all strengths is called Stark effect. Magnetic effects. P. Zeeman was the first person to study the effects of magnetic fields on the optical spectra of atoms in 1896. He observed that the spectral lines of atoms split in the presence of an external magnetic field. Further, work showed that the interaction between the atoms and the field can be classified into two regimes. Weak fields, the effect is called Zeeman effect, and this can be either normal or anomalous. Strong fields, and the effect is known as Paschen-Back effect. The normal Zeeman effect is so called because it agrees with the classical theory developed by Lorentz. The anomalous Zeeman effect is caused by electron spin and is therefore a completely quantum result. In practice, we usually work in the weak field, that is Zeeman limit. The normal Zeeman effect is observed in atoms with no spin. The total spin of an n-electron atom is given by S equal to summation I is equal to 1 to n small si. Only valence electrons are considered, as filled shells have no net spin. Since all the individual electrons have spin 1 by 2, it will not be possible to obtain S is equal to 0 from atoms with an odd number of electrons. However, if there is an even number of valence electrons, then S is equal to 0 states can be obtained. For example, if we have two valence electrons, then total spin quantum number S is equal to 1 by 2 plus minus 1 by 2, and it can be either 0 or 1. In fact, the ground states of atoms of group 2 of the periodic table, which has an electronic configuration NS2, always have S is equal to 0 because the two electrons align with their spins antiparallel. The magnetic moment of an atom with no spin is entirely due to its orbital motion, and it is given as mu is equal to minus mu b in the subscript divided by h cross into capital L, where mu subscript b divided by h cross is equal to E divided by m subscript E and is the gyromagnetic ratio. Interaction energy between magnetic moment and a uniform magnetic field B is given by delta E is equal to minus mu dot P. Assuming B is only in the z direction, the interaction energy of the atom is therefore delta E is equal to minus mu subscript z capital B subscript z. This is equal to mu subscript B into capital B subscript z into m subscript L, where m subscript L is the orbital magnetic quantum number. From this equation, it can be discerned that the application of an external field B splits the degenerate state, that is m subscript L state, evenly. This is why ML is called the magnetic quantum number. The splitting of the ML state of an electron is shown in this figure. The value of L is 2 and it splits into 5 levels when a magnetic field is applied. The effect of the magnetic field on the spectral lines can be worked out from the splitting of the levels, provided the selection rule for magnetic quantum number should be considered. That is, delta ML is equal to 0 or plus minus 1. Consider the transitions between two Zeeman split atomic levels as shown in this figure. According to the selection rule for ML, we can have transitions with ML is equal to 0 or plus minus 1. This gives rise to three transitions whose frequencies are given by h nu is equal to h nu naught plus mu b. H nu is equal to h nu naught plus mu b into bz. This is for delta ML is equal to minus 1. H nu is equal to h nu naught. This is delta ML is equal to 0. And the third is h nu is equal to h nu naught minus mu b bz. For this, delta ML is equal to plus 1. This is the same result as that derived by classical theory. The polarization of the Zeeman lines is determined by the selection rules and the conditions of observation. If we look along the field, that is longitudinal observation, the photons are propagating in the z direction. Light waves are transverse, so only the x and y polarizations are possible. The z polarization, delta ML is equal to 0 line, is therefore absent. Hence, only the lines where delta ML is equal to plus minus 1 transitions are observed. When observing at right angles to the field, that is the transverse direction, all three lines are present. The delta ML is equal to 0 transition is linearly polarized parallel to the field, while the delta ML is equal to plus minus 1 transitions are linearly polarized at right angles to the field. The anomalous Zeeman effect is observed in atoms which possess non-zero spin. This will include all atoms with an odd number of electrons. In the LS coupling regime, the spin-orbit interaction couples the spin and orbital angular momenta together to give the resultant total angular momentum J, and J is equal to L plus S. The orbiting electrons in the atom are equivalent to a classical magnetic gyroscope. The torque applied by the field causes the atomic magnetic dipole to precess around B, an effect called Larmor precession. J precesses slowly about B due to an external magnetic field. Meanwhile, L and S precess more rapidly about J due to the spin-orbit interaction, as shown in this figure. The speed of the precession about B is proportional to the strength of the field. If we increase the field, the Larmor precession frequency will eventually be faster than the spin-orbit precession of L and S around J. This is the point where the behavior ceases to be Zeeman-like and we are in the strong field regime. The interaction energy of the atom is equal to the sum of the interactions of the spin and orbital magnetic moments with the field, and it is given by delta E is equal to minus Z component of mu into Z component of B. This is equal to minus bracket starts Z component of mu superscript spin plus Z component of mu superscript orbital bracket closes B subscript Z, that is the Z component of the magnetic field B. This is equal to the expectation value GS, where S is the subscript, into capital S subscript Z plus L subscript Z bracket mu B upon H cross into Z component of magnetic field, where G subscript S is equal to 2. In this equation, if we substitute Sz is equal to 0 and Lz is equal to MLH cross, then we have normal Zeeman effect. In the case of the precessing atomic magnet, neither Sz nor Lz are constant. Only Jz, that means the Z component of J, which is equal to M subscript J H cross, is well defined. Therefore, firstly, L and S must be projected onto J and then reprojecting this component onto Z axis. The effective dipole moment of the atom is therefore given by mu is equal to minus expectation value of magnitude of L cos theta 1 J upon magnitude of J plus 2 into magnitude of S into cos of theta 2 into J upon magnitude of J mu B H cross, where the factor of 2 in the second terms come from the fact that GS is equal to 2. The angles theta 1 and theta 2 are defined in the figure and can be calculated from the scalar product of the respective vectors. For example, L dot j is equal to magnitude of L magnitude of j into cos of theta 1, and S dot j is equal to magnitude of S magnitude of j into cos of theta 2, which means mu is equal to minus L dot j upon magnitude of j square plus 2 S dot j upon magnitude of j square into mu b upon h cross j. As we know, j is equal to L plus S, so S is equal to j minus L, and S dot S is equal to j minus L dot j minus L. This is equal to j dot j plus L dot L minus 2L dot j. Therefore, 2L dot j is equal to j dot j plus L dot L minus S dot S. So L dot j upon j square is equal to bracket starts j plus 1 bracket closes plus L into bracket starts L plus 1 bracket closes minus S bracket starts S plus 1 bracket closes, and the first bracket also closes, h cross square by 2 whole divided by j bracket starts j plus 1 bracket closes h cross square. This is equal to bracket starts j bracket starts j plus 1 bracket closes plus L bracket starts L plus 1 bracket closes minus S bracket starts S plus 1 bracket closes, and the first bracket also closes, divided by 2j bracket starts j plus 1 bracket closes. Similarly, 2s dot j is equal to j dot j plus s dot s minus L dot L. So we can calculate the value of s dot j by magnitude of j square, and it comes out to be bracket starts j into j plus 1 bracket closes plus s into s plus 1 bracket closes minus L into L plus 1 bracket closes, and the first bracket also closes, divided by 2j into j plus 1. Therefore, mu is equal to minus first bracket starts, second bracket starts j, third bracket starts j plus 1, third bracket closes plus L, third bracket starts L plus 1, and this bracket closes minus S, the bracket starts S plus 1, and the bracket closes. Here the second bracket also closes. This whole divided by 2j bracket starts j plus 1 and the bracket closes plus 2 into square bracket starts here j into bracket starts j plus 1 the bracket closes plus s into s plus 1 the bracket closes minus L into the bracket starts L plus 1 the bracket closes, and the square bracket closes here. This product in square brackets divided by 2j bracket starts j plus 1 bracket closes, and now the first bracket also closes into mu subscript b upon h cross into j. So this comes from where g subscript j is equal to 1 plus square bracket starts j bracket starts j plus 1 bracket closes plus s bracket starts s plus 1 bracket closes minus L bracket starts L plus 1 bracket closes, and the square bracket also closes. This square bracket term divided by 2j bracket starts, j plus 1 bracket closes, where g subscript j is Lande's g factor. Thus mu can be written as mu is equal to minus g subscript j mu subscript b divided by h cross into j. Mu z, the z component of mu, is equal to minus g subscript j mu subscript b m subscript j. When s is equal to 0, g subscript j is equal to 1 because then j must equal L. In this case, the magnetic moment is independent of L, and so all singlet terms are split to the same extent. This uniform splitting results in the normal Zeeman effect. When S is equal to 1 by 2, the value of G subscript j depends on the value of L and S, and so different terms are split to different extents, as shown in the figure on the next slide. The selection rule delta mj is equal to 0 and plus minus 1 continues to limit the transitions, but the lines no longer coincide and form three groups. Thus, the selection rules are delta j is equal to 0 or comma plus minus 1, delta mj is equal to 0 comma plus minus 1. These rules have to applied in addition to the delta L is equal to plus minus 1 and delta S is equal to 0 rules. Delta j is equal to 0 transitions are forbidden when j is equal to 0 for both states, and delta m subscript j is equal to 0 to 0 transitions are forbidden in a delta j is equal to 0 transition. The polarizations of the transitions for anomalous Zeeman effect follow the same pattern as for the normal Zeeman effect. That is, with longitudinal observations, the delta mj is equal to 0 transitions are absent, and the delta mj is equal to plus minus 1 transitions are circularly polarized. With transverse observations, the delta mj is equal to 0 transitions are linearly polarized along the z-axis, and the delta mj is equal to plus minus 1 transitions are linearly polarized in the xy plane, that is the plane perpendicular to magnetic field P. The Paschen-Beck effect is observed at very strong magnetic fields. The criteria for observing the Paschen-Beck effect is that the interaction with the external magnetic field should be much stronger than the spin-orbit interaction. That means mu subscript b into b subscript z, that means that the z component of the magnetic field should be very large in comparison to E subscript SO, which represents the energy of spin-orbit coupling. If this criteria is satisfied, then the precision speed around the external field will be much faster than the spin-orbit precision. This means that the interaction with the external field is now largest perturbation, and so it should be treated first before the perturbation of spin-orbit interaction. Another way to think of the strong field limit is that it occurs when the external field is much smaller than the internal field of the atom arising from the orbital motion. In the Paschen-Beck effect, the spin-orbit interaction is assumed to be negligibly small, and L and S, here capital L and capital S, are therefore no longer coupled together. Each precesses separately around B as has been sketched in the figure. The precision rate for L and S are different because of different G values. Hence, the magnitude of the resultant J varies with time. The quantum number J is no longer a constant for the motion. The interaction energy is calculated by adding the separate contributions of the spin and orbital energies. Delta E is equal to minus mu z into Bz. This is equal to minus bracket starts mu z superscript orbital plus mu z superscript spin bracket closes into z component of magnetic field, that is Bz. The shift of the spectral line is given by delta h nu is equal to bracket starts delta ml plus gs into delta ms bracket closes into mu b into bz. Optical transitions do not affect the spin, and so delta ms is equal to 0. The frequency shift is thus given by delta h nu is equal to delta ml into mu b into bz, where delta ml is equal to 0 or plus minus or plus minus 1. In other words, we revert back to Zeeman effect. The splitting of spectral lines in the presence of electric field is known as Stark effect. In the case of electric fields, the weak and strong fields limits are not normally distinguished, and all the phenomena are collectively called Stark effect. These effects are named after J. Stark, who was the first person to study the effect of electric fields on atomic spectral lines. When he measured the splitting of the hydrogen-Balmer lines in an electric field in 1913. In most atoms, quadratic Stark effect is observed. Therefore, the splitting of spectral lines in the presence of electric field is known as Stark effect. In the case of electric fields, the fields are not divided into weak and strong limits, and all the phenomena are collectively called Stark effect. These effects are named after J. Stark, who was the first person to study the effect of electric fields on atomic spectral lines when he measured the splitting of the hydrogen-Balmer lines in an electric field in 1913. In most atoms, quadratic Stark effect is observed. This linear Stark effect is observed for the excited states of hydrogen and in other atoms at very strong fields. The Stark shift of an atom is harder to observe than the Zeeman shift, which explains why magnetic effects are more widely studied in atomic physics. So students, let us summarize what we have learned in this module. The normal Zeeman effect results from the interaction of magnetic moment due to the orbital motion of the electrons with an external magnetic field. The anomalous Zeeman effect is observed when the spin angular momentum is non-zero and stems from the unequal splitting of the energy levels in the two terms involved in the transition. That unequal splitting stems in turn from the anomalous magnetic moment of the electron. The Paschen-Beck effect arises when the interaction with an external magnetic field is stronger than the spin-orbit interaction. This condition is difficult to achieve except for atoms with a low atomic number and hence small fine structure. Splitting of atomic spectral lines in the presence of electric field is known as Stark effect. If modification of the spectrum is proportional to the strength of the applied electric field, it is known as linear Stark effect. If atoms show a small red shift, that means a shift to lower energy which is proportional to the square of the electric field, then this phenomenon is called the quadratic Stark effect. Thank you.